is about pattern structures and pattern setups for knowledge discovery and complex data.
Okay, thank you. Good afternoon. Добрый день. Есть девайсик для... So I would speak on a model which would exemplify the notions introduced by Professor Osipov before. These models would allow us to represent ontologies of domain and different types of knowledge. Let's sorry. Никак. А как нужно?
Просто, видимо, из фокуса выпал.
Как?
Стрелочка.
Стрелочка. Okay. Okay. This model is based on what people call Galois lattices or concept lattices or formal concept analysis. This is the outline of my talk. And just before we go deep into some algebra and algorithmic issue, I would show you that this has to do with artificial intelligence, because you see our chapter on formal concept analysis from knowledge discovery to knowledge processing was included in this 3 volumes guided tour on AI, which will appear in July in Springer. And also I would like to show you that the applications of the model I will describe to you are really useful in the real world. Here are examples of few patents. American patents, European and Chinese patents, based on techniques I would describe today. And here are just few directions where recent advances in formal concept analysis went in the last decade. And there are deep roots in mathematics, in lattice theory and theory of orders, but I wouldn't speak much on this past. I would start from the basic construction, which is a triple, where the first set is a set of objects, the second set is the set of attributes, and I is a binary relation. Basically, it's a binary relation you are quite aware of, but we call this triple a context, showing that that we're actually speaking of attributes of objects. So this is usual object attribute matrix. Rows stay for objects and attributes stay for their attributes. First, we consider the simplest model where attributes are binary. So here, the object G1 has attributes M1 and M2. And then we have these wonderful definitions of prime operators. For a subset of objects A prime gives you the set of all attributes shared by all objects from A. And dually, symmetrically, for a subset of attributes B prime gives you the set of objects that share all attributes from B. A pair AB is a formal concept if A is equal to B prime and B equal to A prime. Here we see an example of a formal context, formal concept. In a binary matrix, it's a matrix field, submatrix field by crosses, and maximal by inclusion. You cannot add a row or a column without losing the property of being filled with crosses. And here we see examples of how the prime operation works. This is a mathematical definition, but we can use it for the purposes of data science by saying that we have here a subset of objects with similarity expressed through their common attributes. We know that clustering techniques are very popular in data science. And here we have an example of what they call bi-clustering. We don't have any distance on objects. We don't have any distance on attributes, but we express similarity of objects through common attributes. Bi meaning that we have two types of entities, objects and attributes, not just one, as in standard clustering approach. So here's an example, toy example of a context where we have four geometric figures and their properties. And this is a diagram. Some people call it Hasse diagram, but for some reasons I would call it just diagram. Each node of this diagram corresponds to a concept. And the concepts are ordered. And they are ordered by containment of their extents, sets of objects. The larger the extent, the higher it is on the diagram. For example, this concept with the set of objects 1, 4 lies above this one, because this is a more general concept. It can be called in this tiny word the set of equilateral figures. And this is just a square, a sub-concept of this one. Similarly, if we consider this pair, 2, 3, 4, is the class of figures with a direct angle. And this is the subclass of rectangles. This subclass doesn't contain this triangle. And of course, the definition of being a subconcept is transitive. So if this is subconcept of this and this is subconcept of this, then 4 BCD is a subconcept of 2, 3, 4 C. So you can realize that starting from binary data given by this object attribute matrix, or context, how we call it, we can derive a sort of taxonomy of a domain. So taxonomy is an ordered class of, ordered set of classes of objects from the domain. You see, this taxonomy is not necessarily tree-like, like we used to have in natural sciences. We can have multiple inheritance here. And besides this taxonomy, we have another useful tool we can derive using these prime operators, namely implications. I'll speak a bit later on that, but first we formally define the order on concepts. And they have some very interesting properties. As I said, the order describes specialization generalization hierarchy, and the concepts can be used for mining association rules. As you know, association rules are one of the most important tools in data mining. But we'll speak in detail on that a bit later. Let me first go to implications. That's another tool that we have here. And it means an implication between a subset of attributes means that when if we have subset of attributes A, we have subset of attributes B. Here we have a clear case of implication between B and C, because whenever we have attribute B, we have also attribute C. But we come formally to this notion a bit later. First, we dwell into algebraic properties, but they are not just formal, but very useful. Look first at these two properties. If we take a larger subset of objects, then the common subset of attributes becomes smaller. If I take a subset or a superset of objects, then applying double prime will give you also a bigger set. Then application of double prime makes a larger set from an arbitrary subset of objects A. 3 primes equal 1 prime. You can test it using the combination, you can check it using the combination of 1, 2, 3. And then a very important property. Prime of the union is intersection of primes. And if we take 2 subsets of objects, then their common properties, common set of attributes, will be intersection of sets of attributes related to these single sets of objects. We call the double prime operator closure because it satisfies standard properties of closure operator: idempotency, extensity, and monotonicity. So the double prime operators, they map subsets of objects to subsets of objects and subsets of attributes to subsets of attributes. And we call the extent and intent of a concept AB closed because A double prime is equal to A and B double prime is equal to B by the definition of a concept. A is equal B prime and B equal A prime. Yeah? So these are necessary definitions. With this we can move further and formally introduce the notion of implication. I'm sorry, one sign is missing here. A subset of attributes A implies subset of attribute B if A prime is a subset of B prime. So all objects having all attributes from A are objects that also share all attributes from B. Sorry, there should be a subset sign there. The implications are Armstrong rules, known in computer science in its subdomain theory of relational databases. where functional dependencies also obey Armstrong rules. And since we have these rules, we can compute only the representatives, minimal implication base, from which we can derive all other implications using these rules. This can be called a knowledge base of exact knowledge base. And implications are good for modeling analytical dependencies in data, like the following one. If you have differential equations in your course, then you you necessarily had calculus before. Because this is a prerequisite of studying differential equations. But in empirical data, dependencies are not that often. And dependencies are, exact dependencies are not often. Dependencies are more often of statistical nature. And for example, in a hypermarket, an important question is what items are often bought together. If one buys a set of items A, what is the probability of buying B as well? How often one buys A and B together? These questions actually lead to the first papers on data mining, where they defined the notion of association rule. Association rule is similar to an implication, but it is not always the case that when we have A, we have also B. We have it only with some confidence, which is actually the ratio of the number of objects having A and B over the number of objects having A. It's actually conditional probability that having A, you have B. Another measure which characterizes association rule is called support. It's just the ratio of all entries of all rows in your data table where you have both A and B. Recall that G denotes the set of all objects. So it's the number of all rows in your data table. And implications are association rules with confidence 1. Now, let's see how we, let's consider an example of implications and association rules, how they can be found in a diagram of a concept lattice. Sorry, I forgot to say that this ordered set of concepts is not just an ordered set, but it is a lattice, meaning that for every two elements of this ordered set, we have unique supremum and unique infimum, like intersection and union. Now, for these two, the supremum is this, infimum is this. For these two, the infimum is here, and supremum is here. So that's why we call this order on concepts a lattice, and particular name is a concept lattice. So implication B implies C is seen in as follows. The concept corresponding to B, which is B double prime B prime, is here. And it lies below the concept corresponding to C. It is here. C prime, C double prime. So implications are seen in the following way as coming bottom up. And association rules are seen in the opposite direction. We have an association rule, C implies BC, with confidence 2/3, yeah? Because we have 3 cases of C and just 2 of them have B. And the confidence of D implying BCD is D. We have two cases, and one of them is BCD. So it's 1/2. But what about association rule between attributes which where we don't have containment, sets of attributes where we don't have containment? For example, what is the confidence of D implying A? Let's use the properties of prime operators and show that for any two subsets of attributes, the confidence of A implies B is the same as A double prime implies A union B double prime. And these are intents of concepts where one lies above another. Not just an upper neighbor of this, but somewhere above the concept with this intent. And so these association rules correspond to a path from the concept A prime, A double prime to the concept this one. Yeah. More than that, using some simple reasoning, we can show that the confidence of an association rule which stays for a path from some upper concept to a lower concept is actually multiplication of confidences on the way. So if we consider the confidence of C implying BCD, we can just multiply this confidence to this confidence. 2/3 multiplied by 1/2 gives you 1/3. We can check here. We have two ways from empty to AC. Association rule, empty implies AC, means how often do we have AC? We have it just once per 4, and this can be given by 1/2 multiplied by 1/2 or 3/4 multiplied by 1/3, this confidence. So the concept lattice, first viewed as an abstract mathematical object, actually is a very nice, concise representation of all association rules in the data. Usually people look for good association rules with high confidence and high support. So we can, as for confidence, we see that we can store only confidence related to edges of the diagram. As for support, we observe also interesting property that support goes down when you go top-bottom. Top down. This is 1/2, 3/4, 1/2, and the support monotonically decreases when we go down, because the sizes of extents go down when we go down the lattice. So if we want to have association rules with high support, we draw some line, mathematically anti-chain, and above this anti-chain we have highly supported rules, and below it we have lowly supported rules. So we can have this concept lattices as concise representations of association rules. Another example how we can apply concept lattices. Consider this toy example of learning. We have positive examples, negative examples of fruits, and we have some examples where we don't know whether an object is a fruit or not. So we cannot use statistical methods here. Yeah? The sample is too low. So we can judge from similarities only. So we would say that, okay, something is a fruit is it shares some properties with fruits. So we'll try to look for explanation of this target attribute, fruit, to be a fruit, by in similarities of descriptions of objects. So, for example, maybe it's yellow, non-firm, and round. That's probably a fruit because we don't have any counterexamples. But if it is white, then it's likely not to be a fruit. Or it is firm, smooth. Yeah? Then it's also, according to our data, is likely not to be a fruit. So how we represent these similarities? Again, by first binarizing our data. This is our old color attribute, which turned into 4 binary attributes: firm, not firm, smooth, not smooth, round, not round. And then we generate similarities of positive examples which are not defeated by counterexamples. For example, all fruits are non-firm, but this is not a good classifier because tennis ball is also not firm. So we have to take subsamples of fruits, look for their similarities, which are not defeated by counterexamples. So we intersect rows. For example, the intersection of 1 and 2 gives you yellow, non-firm, round, and this looks like a good hypothesis because there are no counterexamples here. But what are intersections of rows? They are actually closed sets of attributes because of the algebraic properties that we considered before, these prime operators. Every intersection of 2 rows or many rows is just a closed set of attributes. So an intent of a formal concept. That's why we can just generate a concept lattice of the positive context, look for interesting hypotheses. So this one intersection of 1 and 2, this intersection on 1 and 4, giving not firm, smooth. This intersection of 3 and 4, giving not firm, not round. But this one, similarity of 2 and 3, gives you just not firm, not smooth, which is falsified, defeated by this tennis ball, which is also not firm and not smooth. So good hypotheses are these 3. They are minimal because we look for smallest condition here. This is condition of our classifier, which actually is if this, then a fruit. If this, then a fruit. If this, then a fruit. In the same way, we can compute hypotheses for negative examples, negative hypothesis. This will be white. If white, then not a fruit. And firm, smooth, then not a fruit. So we have 3 positive hypotheses and 2 negative. And we can make classification. Yeah, with this, for example, this simplest rule, if an example with no not known goal attribute contains only positive hypothesis, it's classified positively. If it contains only negative, classified negatively. Otherwise, we have more subtle situation, and we have to reason statistically. So here we have 3 positive, 2 negative, and we classify mango as a fruit because it contains 2 hypotheses. Yeah, not firm, not smooth, not firm, not round, but doesn't contain any negative hypothesis. So this is, of course, a toy example and a toy model. We can actually, in practice, allow for some small set of counterexamples, both for positive and negative examples, make this classification rule finer. I mean, with this I mean that we also can allow for some containment of hypothesis of the opposite class, but very small ratio. Yeah. We can have parameters controlling this. And I gave you this extreme version, which is quite clear, I hope. So I hope I have motivated you with examples from data mining and machine learning, but we need to have efficient algorithms for computing all these association rules and hypotheses. Unfortunately, concept lattice can be exponential in the size of the context. And counting concepts is a sharp P-complete problem, which means that it's as hard as computing the number of satisfying assignments of conjunctive normal form. Yeah. This actually complexity class is important for data mining problems because we often have many patterns that feed the data, and we don't know even the number of the future patterns we can generate. So one needs still good algorithms. I have it written, but and even pseudocode, but it's hard to follow. I would rather use this example. Recall this subset with 4 figures and 4 attributes. First, we take the first object and compute its intent. It's AD, as far as I recall. And 1 prime makes AD prime makes 1. So we don't add anything here between the first bracket and the second bracket. We add the second object. It gives you the intersection of 1 and 2 gives you A. A prime back gives you 1, 2. So we put bracket here. Then we add object 3, and we get empty intersection. And empty prime would give you the whole set of objects, 1, 2, 3, 4. So we backtrack, and here we can add 4. But when we add 4, we obtain 3. 1, 2, 4 prime makes empty. Empty prime makes 1, 2, 4 free. And we already generated this set, 1, 2, 3, 4, before. But we don't need to go through the whole tree to see that this is a duplicate. We can use this nice property that 3 appears after 4, and that means that we already had the generation before. So here, again, when we backtracked and came to adding 1, 3 prime, then we get 2 and 4, and 2 is smaller than 3. That means that we had generated this before. And so on and so on. And here we have it as well. We add 4 to 2. 2, 4 prime gives you something. This something prime gives you 2, 3, 4. 3 smaller than 4. We had it. So we test duplication locally. And that gives us a nice properties of the algorithm. In the same way, we can add attributes and compute not extents, not sets of objects, but sets of attributes. Why it is preferable? Because for mining association rules, we would like to mine frequent association rules with high support, and they correspond to rules that with premises lying in the top of the lattice. So one attribute objects, sets are most frequent. Then we add more objects, we get less frequent item sets, less frequent sets of attributes. So in the same way, we cross out duplicates using this nice lexicographic trick. We don't need to look that it was generated before. Here, actually, we can detect it locally. And that gives you the following properties of the algorithm. We have unique canonical generation for every concept. Canonical means not crossed out, where the order is respected. This is non-canonical, this is non-canonical. For every concept intent, closed set of attributes, we have a unique canonical generation. There are at most m children of a canonical vertex, because we can add no more than the number of attributes in our set of attributes here, so no more than m children. And we continue the process only for canonical generations. These operations can be computed in this time. So the general time we need to compute all concepts is this. C, the number of concepts, multiplied m squared, g. Look, this is an interesting type of estimate. We used to have estimates of running time based on a function of the input. But as we said before, this function on the input for complexity of computing concepts can be exponential. But we still have to select good algorithms for computing this big number of, potentially big number of concepts. So we take the size of the output inside our estimate. And here it is linear in the size of the output. So if the size is small, then this amount is not big, which proves that the algorithm we've chosen is actually good. As the experts in complexity theory say, we have here total polynomial time, polynomial in the size of input and output, and polynomial amortized time. That means that when we divide the whole complexity by the size of the output, and this is the size of the output, we get polynomial in the size of the input. So we, as data scientists, we have to care about algorithmic efficiency of our approaches. And so here, but not much time left, just 10 minutes. My title was about knowledge discovery with complex data, and I started just from binary data sets. The general idea is as follows. Instead of descriptions given by sets of attributes, we now have arbitrary descriptions with a special operation on that staying for expressing similarity. I will tell you later what similarities is. Actually, it's a partial order where you have infimum for every two elements of the partial order. Let me give an example to make this definitions more vivid. Suppose we have these molecular graphs, and this thing for positive examples of some biological property, say toxicity. And these are toxic compounds and these are non-toxic compounds. What can we say? We'd like to, again, reason by using similarities of objects. If there's some cause of toxicity in their structure, then it should be expressed as similarity of their structure, which doesn't occur in counterexamples. So we need definition of intersection. But if we take intersection of, try to express it as common maximal subgraph, we see that it's not unique. Because even for two graphs, this and this, there are two maximal common subgraphs of these two. Let's see this picture. Oop. I didn't put it in. We have these positive examples 1, 2, 3, 4. And if we take 1 and 2, their common maximal subgraph is this, can be considered as intersection. But common subgraphs of 2 and 3 are not unique. This one and this one. So as intersection, we take all maximal common subgraphs. So instead, set theoretical intersection on sets, we know quite well, we have this new intersection. So intersection of these two sets of graphs is the set containing only one graph. Intersection of two sets of graphs is the set containing two graphs. And so on. Intersection of sets of these graphs gives you the set of two graphs. And we then proceed further by defining intersections on sets of graphs, where we take pairwise intersections from this set and this set, unite them and take maximal by this relation, which is actually subgraph isomorphism relation, which says it holds between two graphs if one graph is a subgraph, is isomorphic to a subgraph of another one. Natural partial order on graphs. And here we can repeat the same story with hypothesis and association rules. So let's start from hypothesis. Remember that we have these positive examples of toxicity, these are negative, these are toxic, these are not. So we take similarities of positive, which are not contained in negative, descriptions of negative examples. So this is good, this is good, this is well, but if we take intersection of 2, 3, 4, which is this subgraph, CH3CCOH, then we see that it is subgraph of a negative example. So it's falsified as a hypothesis of toxicity. So here we have two maximal hypotheses. Two minimal hypotheses. They are maximal in this in the order drawn like that, but they are minimal with respect to description. This one and this one. Yeah? You see, we cannot take this. We cannot take this because intersection of all four gives you subset of graphs, each of which is a subset of some negative example. So these two are falsified, and these are most interesting because they are most general. The smaller the premise of our classifier is, the more interesting it is. I call it premise because it actually corresponds to implication. This implies toxic. This implies toxic. This doesn't imply toxic because we have a counterexample. And in the same way, we can have association rules. For example, this one implies this with confidence. We don't, for computing confidence, we don't need to see these awful things. As a physics student, I had a semester in chemistry, but we applied mathematicians, we didn't like it too much. Maybe some of you also don't like it. But we can compute confidence just using the cardinalities of these sets of objects sharing these descriptions. So it will be 2, the size of this set, divided by 3, the size of this set. So the association rule, this implies this, has confidence 2/3. Yeah? And support 2, the size, divided by this number of all objects, 4, 1/2. So this is, again, gives you a compact representation of association rules. But the problem here is that computing with graphs is much harder than computing with sets. Intersecting sets is reduced to intersecting of binary vectors. This is elementary computer operation. But intersecting graphs is an NP-hard problem. Even testing a subgraph isomorphism is an NP-complete problem. So we need to have some tools of approximation, and these tools are called projection. Formally, projection has some algebraic properties, but we can here give an example of very natural projection. Represent every graph with subgraphs of with k vertices. Here we take k equal to 4, and we get the same structure here, even in with approximations, which is nice. If we don't have much time to work with 4 vertex graphs, we can project even stronger. Take 3 vertex subgraphs, staying for every graph in the initial data. Here we lose some properties, but we still have something meaningful. Here's interesting hypothesis in projected data, in simplified data. That means if we have this, this is a plausible cause of toxicity. Here we don't have a good hypothesis, and this is not minimal hypothesis. So we still have something reasonable. If we project too strongly to 2 vertex graphs, then we get a mess. Yeah? You see, we cannot distinguish anything. So we need to find a trade-off between complexity of representation and reasonable results we can get. Yeah, another, I'm running of time. Just another example. By the way, pharmacology is one of the biggest markets in the world, so these examples with chemistry is very important. But another hot area in modern data mining and data science is text mining. And in the same way as we proceeded with chemical structures, we can proceed with texts. Using some tools for representing text. You know that we can parse every sentence of a text, compute it's parse tree, syntactic tree. But then we lose connections between different sentences in the text. For example, anaphoric relationships, where in one sentence someone is called John, in the other sentence he is called he. Yeah? He and John. So we, in our presentation, we add additional semantic relations between different trees representing a text, and we get what we call parse thicket, чаща in Russian. So we have a text of 4 sentences. These are standard parse trees, and here are semantic relationships between different trees. So, for example, sub-entity, it goes about UNO, United Nations Organization, and some body, here, United Nations, and some body of UNO, it's sub-entity, same entity, anaphora, and so on. And then, if we want to compute similarity of 2 paragraphs, in the standard way, here are 2 texts which are similar, but if we use just keywords, as in standard text mining, we get just some very vague idea. If we compute similarity with parse thickets, we can get common subgraphs of graphs representing these 2 texts. And with this tool, you can get all we had with chemicals and the concept lattices. We can have hierarchical structure of text classes. We can have association rules, like if this substructure is mentioned, then this substructure is mentioned with this and confidence and support. And we can represent learning models as well, like with this toy example on fruits and chemicals. So I'm very sorry, so my time is out. Actually, just one, maybe single word, then how we treat numerical data in the same way. We need to define operation of similarity intersection on rows of numerical values. Let me just have it here. This numerical table, for example, in gene expression data analysis. These are genes and these are proteins, and the number shows the strength of expression, how they call it. So this gene is expressed in this protein in order 8. And the standard problem here is to find similar genes with almost same expressions as in proteins. And intersection of numbers will be intervals that contain the numbers. So 6 and 4 gives you interval from 4 to 6, here 8 to 8, 4 to 5. And in this way we can compute concepts and then association rules, hypotheses, taxonomies, whatever you want. So coming back to the definition, we have set of objects, descriptions, with infimum operation on descriptions, which gives you similarities on descriptions, and a mapping which takes every object to a description. And then instead of primes, we have these boxes. A box is intersection of all descriptions from the set A, And for a description D, D box gives you all objects that share this description. So this description is within description of every object in G. Yeah, and these are like primes, and you define concepts, implications, association rules, hypotheses, and all the rest using the same type of algorithm I described to you. We can compute it in the same way as we compute it with attributes. So sorry, but I have to come to conclusions. So pattern structures offer a concise framework for organizing complex and heterogeneous data. The projections allow to consider large data. And yeah, they are also useful for formalizing several problems applications, like described here. Yeah. And I added some references if you want to look deeper in this area. You're welcome. Thank you for your attention. If you have questions.